This is Jamie Jacob in Houston, Texas at the American Meteorological Society annual meeting, where we're seeing the latest and greatest in weather research, including observations, forecasting, integration of artificial intelligence. You can name it. If it's related to weather and the climate, you can find it here. This includes a lot of groundbreaking technology in new observational sensors, everything from radiosondes to LIDARs, including uncrewed aircraft systems. So the irony is not lost on me that I was delayed in getting here due to Winter Storm Fern, but I was able to navigate around that weather obstacle. And here I am taking a look at a lot of the latest technology, particularly as that is related to aviation weather and everything that we're doing at OSU, OAir, in Oklahoma for improving weather forecasting, reporting, and getting the word out about severe weather. So let's go take a look.
So, hi, I'm good. Welcome to our Meteorologics booth. Here you see our 6 kilometer drone. So this is a hexacopter drone that flies up to 6 kilometers height and measures temperature, humidity, pressure, wind speed, and wind direction. This is our current model.
So 6 kilometers,
Yes.
right? What's that in English?
In feet, you mean? This is a very good question. Is it 20,000 feet?
Yeah,
20,000 feet. Okay. Sorry, I'm from Europe.
That's all good, right? So we're doing this for international good participants as well.
Okay.
So this is the model that we have.
Exactly. Yes.
Right? So can you tell a little bit about how we obviously the thermodynamic properties are measured by the sensors on board. How does it calculate wind speed?
No. So as you see, the drone is very symmetric. So it means that no matter from which direction the wind comes, the drone has the same resistance to wind. And what it does, it actually leans into the wind to be able to withstand it. And within the drone, we have sensors who measure the attitude of the drone. And from these sensors, we can then calculate the wind speed and also the wind direction. You're welcome.
So let's take a look at the media slide.
Yes. Follow me. So here we go. This is our meteor glider. We can hold it like this so I can read it. So this is a very small glider that you can attach to a normal weather balloon, and then you can just release it like a normal radiosonde, and it will go up to 30 kilometers or whatever altitude you want it to go. And then once it reaches its target altitude, it will release from the balloon and come back to the launch site or whatever point you set where you want to have it back. And in front of here, you have the radiosonde inside. Here you have the measurement device. And as you see, the wings can like move a bit, so it can actually steer its way down to its launch site where it has to return.
Excellent. So in theory, you can launch two of these from the same point.
Yes, you could.
And have them return to different locations.
Yes, you can. Yeah, you can all predefine this in like a simple web interface.
So it's measuring the wind on the way up, and it uses that as part of its trajectory calculation.
Yes, but it also uses the Meteorologics API weather data. So we have this also, of course, in our system. Yeah, and here you can see the like some screenshots from our weather models. Yeah.
Excellent. All right. Thank you very much. We appreciate it.
You're welcome.
So it's not just having a Series 7, you have to jump through all kinds of
There's additional layers of review and approval. Right, so you have to do the FAA parts and be trained by the manufacturer and everything. Yep. And then there's additional restrictions. And so it's something that's one of the things that's...
Whenever you're ready, I'll you.
So we're happy to introduce the CopterSonde 3.1. This is still a prototype, so forgive a little bit unfinished look of it. But we got a couple of new features that we're introducing. Instead of all 3D printed shell, it's now a mix of carbon fiber on the sides and a 3D printed material on the top. It's a slightly different material than we used for the Copterson 3. Stronger, more durable, and more weather resilient as well, especially in those extreme temperatures of heat and cold. Still have the same carbon fiber arms. That's a really important requirement for durability and the lightweight of the system itself. We've got new motors from a company called Vertec. These are going to be, this is just a test version. These are not going to be the final motors that we're using, but the brand is the same. They're going to be a lot more powerful, and we'll use different propellers that are going to be longer as well. So that's going to be able to provide more thrust, and ideally, hopefully, fingers crossed, higher altitude and longer duration, longer flight duration. You can see the configuration of the drone is pretty similar, but a lot skinnier profile. So if I hold these two up next to each other, you can see the difference of the width of this one versus that one. So it's a little bit taller. We also moved the GNSS outside of the body of the aircraft. That's going to reduce the amount of EMI, so ideally better GPS performance and reception. The front shell is still going to be the place where we house the sensors. We have a slightly smaller but more powerful fan that's going to be drawing air across those sensors, giving it good aspiration. And the battery cavity is in a similar spot here. So some really exciting advancements for the Copterson 3.1, and we're ready to take your order for a minimum of 10 units.
Fantastic.
Whenever you're ready.
All right, well, when can we expect to see this on the market?
So the plan is to have it ready by third quarter of this year, and we're hoping to have it done in time to fly at ISARA in Florida.
Fantastic.
So
all right.
fingers crossed.
We're gonna, cross our fingers that it's gonna happen.
Yeah.
Look forward to seeing it.
Yeah, absolutely. Thanks, guys.
I guess so. Hey everybody, this is Tony Segales, researcher at the University of Oklahoma. And what you're seeing here is the Copterson. This is the latest cutting edge technology that we've developed at the University of Oklahoma. And we are aiming to use this drone for optimal weather sampling, profiling of the boundary layer to fill up the gap, the observational gap that we usually see in the numerical models. And the future is bright. We think that these drones can really do the job and give a better picture of how the forecast weather could look like. So stay tuned. This copter will come to you.
That's fantastic. Good job. So, and this was initially started under the NSF cloud map.
Yes. So this all started with the cloud map NSF a few years ago. So we started with a really nice model, and then from there we evolved through the field campaigns that we were having every year. Every year was a change, an iteration. This drone literally is shaped by weather and shaped by all the field deployments we've made so far. And now NOAA is supporting it a lot. NOAA, National Severe Storm Laboratory, we're all in to have a better design for the future.
Fantastic. Thank you, Tony.
Yeah.
So among the many participants we have here at AMS includes NASA, a lot of industrial partners, but of course we also have our premier weather agencies, which includes NCAR, the National Center for Atmospheric Research, longtime partner of us, James Pinto, for example, works here in the Aviation Weather Office, primarily focused on developing models. And then, of course, NOAA over here. NOAA having many different components across the country, including the National Severe Storms Laboratory. So if we take a walk over on the NOAA side, and notice NOAA does both atmosphere and ocean. That is the up here in NOAA. And so we work with them for both our atmospheric science measurements as well as working with our friends in the ocean. We don't do any sea turtle work, but of course we do work with dolphins. But we have our National Severe Storms Laboratory, which is one of our partners that we work with out of Norman at the National Weather Center. And this is an example of Sean Wah's vehicle storm chasing system that he has set up. Mobile mesonet capability and system set up here, but with the new hail camera, right, which is designed to be able to capture hail in real time as it's falling to understand the dynamics of how hail is actually formed. Think about hail as in essentially freezing precipitation, and as it goes to different layers and builds up, there's still a lot we don't understand about how hail actually forms. And by the time it hits the ground, it already starts to melt. So this captures it in real time using this camera system. So examples of a lot of the great technology that's being developed here and showcased at AMS.
Yeah, this one is a great example of like today.
Is this live right now?
Live, yes. So
It's
this
exciting.
one has just taken the sounding off the coast of Morocco, and one right here for the Atlantic, and the second one here is right off the coast of Morocco, around 15 to 1.7 kilometers. Yeah,
That's exciting.
very exciting.
Very impressive.
And then we do our own forecast model. So we have our own AI-based forecast models, running every 20 minutes, and simulating data live from that forecast.
So are these all your own systems that you're operating, or these are some of the customers?
No, we all operate those. The data gets sold, but we operate it.
Okay.
So we have 14 launch sites globally right now, and yeah.
So you're saying?
Yeah, so this is the FM antenna, 400 megahertz. That's a dual band GNSS, so L1, L5, so you get twice the accuracy for velocity and altitude. NFC, so you don't need any connectors, you just take it to an NFC, and then that's a transmitter, and then the sensor boom with the pressure, temperature, humidity, ambient light sensors. There's visible light, infrared, and UVB.
Really?
That's really nice for detecting clouds.
That's really great. That's
Then I
nice.
have a 3D accelerometer and gyro here, so you get the motion. And
What's your accuracy on the rate?
so we're sampling at 2 hertz internally. But the accuracy is it's plus minus 4G for the accelerometer, plus minus, was it 2,000 degrees per second for the gyro, and then there's a magnetometer as well, 3D.
It's fantastic. And it communicates all with the base station. You can
Yeah.
do 50 of these.
50 of these simultaneous, yeah, 50, 50.
That's really exciting. So,
It has, thanks to you, it has.
take it away.
Hi, my name is Diego Gomez-Folk. I am a graduate student at the University of Colorado, advised by Professor Brian Argro. This is our workhorse aircraft, the Raven. It's a UAS. It's built on sort of commercial off-the-shelf avionics with some custom autonomy thrown in the mix. It's built basically as a long-endurance platform for atmospheric sensing. It carries 2 Vaisala RS-41 radiosonde sensors for pressure, temperature, and humidity,
and then also has a custom designed in-house multi-hole probe for three-dimensional wind sensing. We get all three inertial wind components at about 10 to 20 hertz, depending on the campaign. We also has about a 5-pound payload. It can carry basically whatever payload you can imagine that can fit in there. We've carried camera systems, particle spectrometers, interferometers, IR sensors, fine wires like hot wires for turbulence sensing, and yeah, all kinds of other stuff. We use it primarily for sort of mobile sensing of moving atmospheric targets, but it's also been used for boundary layer profiling for evolving features. We think one of our unique capabilities, in addition to our endurance, is our capacity to go out and target features as they move. You can imagine setting up a tower is easy if you know exactly what you're looking at, but if it's a mobile sort of feature, you want to be able to go out and get it. We have COAs in, I think, 30 states, the ability to fly up to 2,500 feet legally, and can operate 2 or 3 aircraft at a time, depending on staffing. Yeah, we are now a community instrumentation facility, so you can consult with us to go out and take measurements.
That is fantastic. I didn't know about that last part.
Yeah, we are. It's new.
All right, everyone. Thank you very much for your time.
And shout out to my advisor, Professor Brian Argro, and Professor Eric Frew at the University of Colorado. And I enjoyed your talk on the Tulsa flights and the mode coordination. Of course.
Thank you.
Hey, thanks for stopping by. Feel free to take a flyer.
Okay, this is part of a larger project to study the potential implementation of drones in the routine meteorological observation network. And so the first effort was focused on vertical profiles up to 2 kilometers. This is focused on horizontal transect. So the technique we're using is called an OSSI, where we take a simulation called a nature run, and we treat it as the truth. It's high resolution. It has all the physics, dynamics that you would expect from the atmosphere. We treat that as truth, and then we run a forecast model initialized from that nature run, and evaluate whether new platforms, in this case UAS, actually improve the forecast compared to conventional observations. So if you imagine radiosondes or ASOS, surface observation stations, or commercial aircraft operating in the atmosphere, we take those data, but not the actual data they collect. They're interpolated data from the nature run and assimilate those into the forecast model, and we run it forward. And you're going to get a difference between the forecast model and the nature run, as you would expect. But then we put in drones and we see if we can close the difference. We can reduce the error between the forecast and the nature run using UAS. And there are a lot of ways that you can operate drones. We tried vertical profiles up to 2 kilometers, and we have really good results with improvements of 20, 30, 40%, depending on the density of the network. And so the next step is to fly them instead of vertical profiles, but fly them horizontally. So we take all these different densities, not at once, one at a time. These are all the drones, and we essentially fly them horizontally. They land, we fly them horizontally. So every few hours for the 300 kilometer spacing, and every hour for the 35 kilometer spacing, we have a new set of drones that are launched. And so we assimilate those data, we see what the impact is relative to the control run, but we can also compare it back to the vertical profile. So if it turns out that this modality of operation produces better results than vertical profiles, it tells us something about how we prioritize the implementation of drones into the weather observing network.
So, upshot, right? If you had a choice between profiles and transects, which would you choose?
So that's what hopefully this will tell us. I mean, in terms of Kona scale improvements, this should give us an answer. It won't give us the complete answer because it may depend on the weather. So it may be that in certain circumstances you want to fly vertical profiles, in certain circumstances you want to fly horizontal transects, maybe you want to fly a mix of them. And so this is really kind of the heavy-handed bulk approach, and you have to start here, and then we can say, all right, what happens if we change this so that we're only flying in particular areas? So areas where we think horizontal profiling would be more impactful. So instead of taking 300 drones and flying them everywhere, we take 300 drones, put them in places that we need them the most, fly them, assimilate those data, and ostensibly the result would be improvement in the forecast over just flying them everywhere at once.
So rather than having uniform density, you can have sparse population in some areas and really dense population
That's right.
in others.
So you take advantage of the high density where you need it most.
And although this looks crazy dense, right? If you compare this with like our radiosonde launches.
That's right. The radiosondes are even less dense than this. Yeah. So a student who's doing the full tropospheric observations to test essentially the same thing, but not in horizontal, just deep tropospheric as opposed to 0 to 2 kilometers. Now you may ask the question, well, what does it matter? If you're flying them at the same locations as radiosondes like he's doing, why would it matter whether it's a radiosonde or a drone? But the beauty of a drone is that you can launch, collect observations on the way down, which you don't do with a radiosonde, and then immediately relaunch. So we could do hourly profiles with drones that you can't do with radiosondes. So same density, but a much higher, 12 times the frequency of radiosondes.
What's next?
What's next is actually get results, because I don't have any results from the horizontal transects. Get those results. The next step after that is, besides publishing all this, is to do the targeted observations. So we have a grant funded to do the targeted observations where we put them in places that they're needed most and rerun the set of experiments.
This is where posters go to die. Much like an elephant graveyard, unwanted posters end up here at the end of the day. Their job done. Knowledge transferred. It's been a great meeting here this week in Houston at AMS, even though I was only able to attend about half of the meeting. I've seen so many great talks with fantastic implementations of new technology, such as autonomy and AI, and how that's improving our observations and forecasting capabilities. But lots of great meetings and met plenty of old friends, and such as Fred Carr here, Grand Poobah, of the Oklahoma Mesonet, still the world's premier Mesonet capability, but also great budding partnerships and relationships with other folks, such as the New York Mesonet site, and all the fantastic partners we've had with CloudMap and WidMap in the past, and of course, new projects that are developing. It's really exciting to see what's going to come out of this. We definitely need to have a greater presence here next year, weather permitting. It's amazing how quickly Houston shuts down when it gets slightly below freezing. Of course, next year we'll be in Denver, and so I think they're more well equipped on handling the severe weather that you might see in January. Of course, they've got no snow. It all came to Oklahoma this year. So I'm going to finish my last morning here with final sessions. So until next time.
There was no F-bombs.
Yeah, you're supposed to use them appropriately.
But there was no appropriate way.
Drinking